Okay, so welcome to this next video in which we are discussing the endothelium-dependent hyperpolarization and the possibility that nitric oxide is an endothelium-dependent hyperpolarization factor. Okay, so we've seen how Tar et al. In 1990 seemed to show that nitric oxide was capable of repolarizing these smooth muscle cells which have been pre-constricted or pre-contracted by noradrenaline treatment, which also causes the depolarization of the cell membrane because we're releasing the calcium into the cytoplasm from the SR. Okay, so we're going to follow up this story. In 1993, okay, 1 year before I was born, Parkinson et al. Did an experiment which was building on Tar et al.'s experiment. So Parkinson et al. So what did these guys do? Well, basically, what they did was they continued what Tar et al. Had done. So they took they took blood vessels. So let's say here is our blood vessel, which they had pre-treated with noradrenaline. So they have got these smooth muscle cells to contract hugely, basically. So the blood vessel is as constricted as it possibly can be. In addition, all of these smooth muscle cells are slightly depolarized if you measure the electrical potential difference across their membrane. Right, now, what we're going to do is we're going to use the nitrovasodilators. So we're going to use sodium nitroprusside, SNP for short, and we're going to use maybe glycerol trinitrate, whichever one is your preferred nitrovasodilator. We're going to put one of these in. It's going to produce nitric oxide, and what we should see, if Tar et al. Is right, is we should see a slight repolarization of the electrical potential difference across the membrane. So if we plot voltage against time on a graph, and remember, by voltage I mean the voltage from extracellular to intracellular, then maybe initially it's somewhere here. So this is a slightly depolarized electrical potential of what you would have been if the smooth muscle cells had not been pre-treated by noradrenaline. Okay, and then when you apply the nitrovasodilator, so when you apply, let's say, sodium, not STN, SNP, sodium nitroprusside, what's going to happen is you're going to produce this nitric oxide, it will go to the smooth muscle cells, and if it produces a repolarization, we should see a downward deflection, and indeed, that's what they got. They were able to reproduce Tar et al.'s results, but they went further, they didn't just stop there. What they were able to find is that if you were to stretch the blood vessel, okay, so if you were to pull this side this way and pull this side this way, don't break it, but stretch it a little, like one of these ancient torture machines. Okay, stretch the blood vessel out a bit, and then do the same experiment again. So again, you start off at this same resting membrane potential, and then you apply the sodium nitroprusside. What you would get instead is a bigger repolarization, okay? And then as the sodium nitroprusside is washed out and there's no more nitric oxide again left over, you'll go back to that same starting electrical potential difference, which is due to the presence of the nitric oxide, the presence of the norepinephrine that you're bathed in. So basically, if you stretch the blood vessel, the repolarization that you see as a result of nitric oxide is greater. Okay, and what they were also able to do was they were able to look at the response that you got to acetylcholine and compare it to the result that you got just from one of the nitrovasodilators. So now, let's look at what response you get to acetylcholine. So these are both just nitrovasodilators. So I'll colour these in. So green and pink, they are both to nitrovasodilators. Green is before you stretch, pink is after you stretch. Now, let's look at the response that you get to acetylcholine. So this time what we're going to do is, instead of applying sodium nitroprusside, we're going to put in acetylcholine. And maybe I should draw this on a separate graph. Okay, so that that one doesn't get too busy. So again, you start off down here somewhere. So the same electrical potential difference, because it's the same artery, well, it's the same artery which has been pre-treated with noradrenaline to produce this depolarization of the electrical potential difference across the membrane. Now what you're going to do is treat with acetylcholine. Okay, now what you see in the case of acetylcholine is a quite different response. You see something that looks more like that. So you treat with acetylcholine, it comes in, acetylcholine binds to the M3 receptors on the endothelial cells, triggers a calcium signal within the endothelial cells, which activates the eNOS enzyme, and then causes the production of nitric oxide, which goes to the smooth muscle cells and produces relaxation, but also repolarization. But that's our theory. But this looks very different from the response that we get from the nitrovasodilator. And in fact, what they were able to show is that if you did treat this, this blood vessel with an eNOS inhibitor, and they, I think, used L-name rather than LNMMA, but it's very similar. So L-name stands for NG nitro, L-arginine, and then methyl ester. So I'll just show you the structure of this, just to convince you again that this is a this is an analog of L-arginine, and that's how it's going to inhibit the eNOS enzyme. So the structure of it then is that if this is the amino group of the amino acid here, okay, so it's an analog of L-arginine again, so it's an analog of an amino acid. Okay, then here's the alpha carbon. Here's the carboxylic acid group. Okay, but it's not as a carboxylic acid group yet anymore. It's a methyl ester. So this carboxylic acid group has been turned into an ester with a methyl group there. Okay, so it's basically been esterified to a methanol group down here. Okay, and now the R group of this structure here is also modified from L-arginine's R group. So it's not just L-arginine with a methyl ester. Instead, you've also modified the right end of the R group. Okay, so here are these three methylene groups, followed by the nitrogen, followed by the carbon, and then you've got this amino group, but now the amino group has had added to it a nitro group here. Okay, like so. And you still have this carbon double bonded to a nitrogen with a hydrogen off it there. So this is the structure of L-name. Okay, so NG nitro L-arginine methyl ester. Right, so this nitro group here, what is happening here? This is a complicated chemical structure. Basically, what happens is nitrogen has a lone pair of electrons on it. Oxygen has two places. Well, oxygen atoms want to gain 2 extra electrons. So effectively what's happened is the nitrogen has provided both electrons into this bond. And in doing so, effectively it's donated one of those electrons to oxygen and kept one for itself. In so doing, it's become positively charged, oxygen's become negatively charged, and then what's happened is they've both formed a covalent bond. So oxygen, with its newly acquired electron from nitrogen, forms a covalent bond with nitrogen effectively, and that's how they get these negative and positive charges. So let me just show this. So here's nitrogen with its lone pair here. Here's oxygen with its 3 lone pairs, but it doesn't want to use those. They stay behind it. So basically what's going to happen is nitrogen's going to give one of these electrons to oxygen, like so. So that's moved like that. And now they're going to form a covalent bond where they share these 2 electrons, but that means that the oxygen has a negative charge and the nitrogen has a positive charge because of the initial movement of that electron. Okay, so that's what you've got in this nitro group here. And that's why the nitrogen's got a positive charge and the oxygen a negative charge. Now, if you use L-name on this system and then do the whole experiment again, i.e. You provide the acetylcholine, that stimulates the M3 receptors on the endothelial cells, They produce nitric oxide, and that goes through to the smooth muscle cells to cause this repolarization. What you see is an almost identical response when you inhibit with L-name, okay, but then it looks like this instead. So L-name is this inhibitor of the eNOS, so it will stop the endothelial cells producing nitric oxide in response to the acetylcholine. So if our repolarizing response was purely down to the nitric oxide, we would have expected this to be completely gone. We have not seen that. We've seen that it's reduced. This end bit over here is reduced, okay? And basically, that's what we think. There are two portions to the endothelium-dependent hyperpolarization. There is this early portion here. This is the early phase, or the fast phase also, early/fast phase, which basically seems to be nitric oxide independent. It does not require nitric oxide, and somehow the acetylcholine is working for a mechanism that we haven't discussed yet, that we don't know. We're going to have to continue the story to find out what this is, but it's working through some other mechanism, and this late portion, or this slow phase over here, this is produced by the nitric oxide that the endothelial cells produce. So the nitric oxide is only in part responsible for the repolarization that you see of the electrical potential difference in response to acetylcholine. It's responsible for the late or slow phase. It's not responsible for this early or fast phase, and we don't know. I haven't told you yet what is responsible for this early fast phase, and it's still not a simple story. There are loads of different things that could be contributing to this, but we will find some satisfying answers to what is responsible for this early fast phase. So, to conclude then, what Parkinson et al. In 1993 have shown is that the repolarization that nitric oxide produces of the precontracted smooth muscle cells in a blood vessel is dependent upon the stretch of that blood vessel. In addition, nitric oxide seems to be only responsible for the late or slow phase of the repolarization. It does not seem to be responsible for this early fast phase, and that's shown by the fact that if we inhibit nitric oxide production by the endothelial cells and then stimulate with acetylcholine, we still get this early fast phase of repolarization of those preconstricted smooth muscle cells, electrical potential differences across their membranes, but we don't get the slow or late phase. And that slow or late phase therefore seems to be as a result of the nitric oxide production by the endothelial cells, but the early fast phase doesn't. So let's continue our journey in the next video, where we'll begin to explore other mechanisms underlying endothelium-dependent hyperpolarization.